All right, fantastic. Let's get started. Back into it again. I think we are on lecture 6. Am I right? I think so. Raise your hands who's been here every session so far. Yes, 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 yes. Fantastic. I love it. I love the enthusiasm. There's a lot of stuff that we're getting through, and a lot of it's getting complicated. Warning, today is going to get a lot more complicated, but we have plenty of time to do it. And what I want to spend most of today doing is basically tackling the repeated error of this matrix is the wrong shape. That's what we're going to do for a long time today, hopefully. And by the end of it, it should be really clear what shapes things should be and how you need to change your code to fix that. And we're going to do this all in the context of building a language model. Some of you might have heard of language modeling, especially recently. Can anybody help me define what that is? Language modeling. Any suggestions? Can everybody give me an example of a language model? All heard of one. ChatGPT is a language model. Yep, GPT-3 is a language model. There are lots of different language models out there. And what do they do at a high level?
Imitate human language?
Imitate human language, yeah, that's a good way to put it, yeah, and specifically like generating text in this case. So they're generative models. That means they can generate data which looks much like the distribution of the training data that they'd seen when they were learning. And as a result, once they've got that understanding of the internal language, they can produce more data like that. So how do they work? Well, the first thing we should look at is in this notebook. It's the clue is in the name here. What are recurrent neural networks? But if you open up this notebook, the first thing we should look at is let's dive back to the sequential data we saw yesterday, understand how that's represented, and then we'll have a go at figuring out, okay, what are the limitations of the neural networks we looked at so far for tackling that kind of data. So if you want to pull up that notebook, I'll just dim the lights. All right, cool. Let me know. It's up a little bit, yeah. That's low. This is medium. How's that? Still see? Cool, good stuff. All right, cool. So this is me trying to be specific about what the sequential data we're going to work with today and the sequential data we looked at yesterday should look like. So we've got each of these different examples now. And previously, where the examples were just vectors, each number representing a different feature of that example, now you've got another dimension introduced, which is this time dimension for sequential data, right? And that's because sequential data, like audio waveforms or text data, or maybe the price of a piece of artwork over time, they have some features at different steps in time, and those features might vary through time. So what we're looking at here in this example on the left is a generic example, example I. It has t different rows and n different columns. The first dimension t represents how many time steps were there in this data. How many time steps were each of these n features in the columns recorded over. So that's how we can represent this sequential data numerically. And regardless of what the type is, whether it be, like I said, the price of something over time or words, we should be able to represent it in this format. It's going to have at least one extra dimension, that time dimension. So a simple example over here, almost trivial example, would be each of your inputs has 2 different features, and over time, you can see those features change. So this green one here is feature number 2, because it's in the second column, at time step 3 for example number 4. And then down here, we've got another example as well. So in the case of natural language processing, and thinking back to what we saw when we looked at word embeddings, what would this column represent? What would the number of columns represent when you've got text? The size of the embeddings, exactly, yeah. So if I've got 128 dimensional embeddings, that's going to be the number of columns I have for each example. And what would the length of the sequence represent? Let's say I'm doing a a sentiment classification problem where I want to classify if a sentence is positive or negative. What does this first dimension for an individual example represent? I've got Amazon reviews. I want to know whether they're positive or negative. What is that first dimension? The number of columns is the dimensionality of each word or each token. The number of words or number of tokens, yeah. So this individual example length in the case of natural language processing is going to be number of tokens by dimensionality of the word embeddings. And so we'll need to figure out a way to take our raw text and turn it into that format, but that should be fine. And if we can get it in that numerical format, then it should be somewhere close to where we need it to be able to process with neural networks, or with any mathematical model, really. Any questions about that? Here's another visualization for you. That's what an individual example looks like. So the blue bounding box, that's just the whole example, one sentence, let's say. And in this case, it's got 4 different vectors in. Each of those 4 represents the features at a different time step. And in each of those time steps, you can see the gray nodes are meant to represent different numbers. So you've got different numbers for different features, and you have the same thing at every different time step as you go forward. So as long as that's clear, then we should be good to start exploring how to write some code very shortly.
I'm sorry, so is it the same, let's say, sentence or word being passed through the neural network multiple times? That's why we have time step 1, time step 2. Like, what is?
So we're just talking about the raw data here. No model has been used yet. Just purely, if you have a sentence and you want to represent it mathematically, what's the way to do that? And so it would be this matrix where you have as many you have tokens for each different time step, and each of them have many different values in the embedding. So,
like, how is this sentence changing over time?
well, each of those is a word. Sorry, each of them is a token. So when we talk about the time steps of a sentence or a body of text, we're just talking about the different tokens.
Okay,
So
word by word by.
yeah, so this is word number 1, word number 2, word number 3, word number 4. In the case of natural language processing, those orange vectors, they're embeddings. So it's the embedding of each of those words. Is that clear?
So each word is represented like a series of numbers. So yes.
Exactly. Yeah.
And the sentence which I want to represent is a time series. So
Exactly.
first word, last word, and that's it.
Exactly. Here we got a sentence which is 4 tokens long, and that's why it's represented like this. Embedding for each token. Token number 1, word number 1, and so on.
Okay.
This is great. Let's get this dialogue going, because it's very easy for me to miss things like that, and very easy for you guys to reintroduce them. So any point, bring it back in. Just shout out and we can go through it. But this needs to be clear before we start looking at the data, okay? This is how it's represented. So what's the shape of a batch of data going to be? Remember that our neural networks, we pass in batches at a time. That is a group of examples at the same time. What's the shape of that going to be?
The time series like shape, so it's going to be a matrix with an extra dimension on the batch.
Yeah, it's going to be the shape of this, but with an extra dimension on the front, which is the batch size. So yeah, we'll look at some specifics of that basically, but it's going to be a tensor with now at least three dimensions in this case. First dimension is going to be how many items in this batch. Maybe I've got batches of 16 sentences at a time which I'm processing, and then each of them is going to have a length. Maybe use 30 tokens length for what we'll be doing, and then each of them has an embedding which is maybe 128 dimensions. So you'd have a batch size by length by embedding dimension size tensor input as your batch. Okay, cool, fantastic. Any other questions about that? Cool. Can I get some examples of sequential data? I've mentioned text, obviously. Music, absolutely. What would the format of that be? MP3? Yeah, but what would the dimensions be? In this case, what does the time represent? Maybe what does the vector in the middle represent?
Like, so it's gonna be like an audio wave?
Mhm.
Is it like, so it would be like frequency of sound versus like the rest of the light?
Mhm. Yeah, so in that case, time would be literal time.
Uh-huh.
So it's, okay, at the first millisecond, second millisecond, so on, whatever the sample frequency is. And then each of those individual representations at that time step is probably going to be, like in the simplest case, I guess it'd be like frequency amplitude, but in the more complex case, it would probably be like a spectrogram data. And that would be 2D, actually. So that vector, that representation would be 2D because it has, yeah, I think that's how spectrograms are represented. So that's an interesting point, right? Is that these representations, they could have more dimensions as well. It could be that you're processing images over time, aka a video. And in that case, again, each of those individual representations at that time step, this x1 here, that would be a frame of an image. So it would have at least height and width if it was grayscale. If it was color, it would have a third dimension as well. So in that case, you'd have a 4-dimensional feature for every single example, and then you have the batch dimension as well. So just the idea of how this can extend into bigger examples. But this is a simple example where just time and embedding size. Any other examples of sequential data? Stock prices, yeah, what would that look like?
Price versus time.
Yeah, so time again on the axis, and then that vector, what would that be?
It's scalar.
Yeah, it could be a scalar of just one stock, or it could be a vector of lots of different stocks in their price, or it could be a vector of maybe not just the price, but other attributes as well. Whatever that would be. Cool, great examples. So, to move on from here, I need to highlight that we're going to have a problem when we try and process this with a neural network, right? Which is that the feed-forward networks we looked at previously, they all expect vector inputs. And this is clearly not vector. So I would need to maybe firstly turn it into a vector. But there's a problem, there's a few problems with that. And one of them, well, can anybody give me any of the problems? If I were just to take, okay, I've got a bunch of different sequences, flatten them all into a vector, assure it to pass that to my neural network. Problems with that?
Are you plotting all of the sequences into a vector, or
Each sequence into a vector, so it would have the same as our previously, where we had, for example, an image flattened into a vector. Actually has one of the same problems as flattening an image.
Your matrix doesn't have a fixed size.
Exactly, yeah, that's one of the key issues there. Different sequence lengths, different size inputs, and the feed-forward networks we looked at, they only process fixed size inputs.
So if your data that if you have like frames of an image, you can use locality data in both similar frames, so you might be able to run that surface convolution might not run as well.
What do you mean they might not run as well?
So as an example, if you have 2D convolution, you might lose some data about like the individual positions of the pixels if you flatten it down to a single layer.
Yeah.
So that was one.
Yes, exactly. So when you have a great analogy here, the image data is when you flatten an image, you throw away a lot of the spatial information, or at least the model has to learn to extract that out after it's been flattened. And the same is true here. If we flatten this all into one vector, then what does the dimensionality of your example represent? It represents like a combination of time and different features, which is just like a bit confusing. It would make sense they have their own axes, because that's the natural format of the data, right? And what you want to do as much as possible is use what you know is true about this data and take advantage of that, instead of throwing it all away and treating it all as the same, right? For example, images have spatial information, so you should take advantage of that spatial information. And very similar to spatial information is sequential information. So you should not throw that away, because that is actually where a lot of the information is stored. It's in the relationship, in the positions between items in sequences or in space. So that's certainly going to complicate things. And another issue, which is similar for vision, is that if say we do flatten out an image, or let's stick with sequences. If you flatten out a sequence, you want to look for the same kind of patterns in a sequence in different places across that sequence. So if you imagine we've flattened this all out into a vector, and that's the input to one of our feed forward to the first layer of a neural network, well then, if I'm looking for something in the beginning of the sequence, the weights at the top of that layer are going to have to learn how to detect that thing. And if I want to look for that thing later in the sequence as well, I'm going to have the weights near the bottom of the first layer learn to also detect that thing. So you have the same weights, maybe looking for the same, you have different weights looking for the same things. And what would be much nicer is instead just to share the weights, which basically looking for a certain pattern, across time. So that's what, and that's one of the key things that these recurrent neural networks will look at. That's the way that they exploit this sequential information. So just to highlight that again more clearly, let me find you a good example of a neural network, which I've got in here somewhere. And let's imagine this one. So let's imagine we've got this neural network, and we take our sequence and we flatten it out like this. So let's say we're looking for a particular pattern. Maybe it's like it's a preposition followed by an adjective, something like, he ran or she ate, something like that. Those kind of combinations of words is a combination that we want to look for. Remember that the weights, which combine layers, all they do is they combine features in the input layer to come up with a new number, which represents, hey, is this thing I'm looking for, is it present? Is it there or is it not? If it is there, then this number will be high. It says, hey, there's that pattern I'm looking for. There's that preposition followed by an adjective, it slept, whatever, something like that. And so these weights that would combine those features at the beginning, you would also have to have the same weights, aka looking for the same pattern, looking at the end of the sequence as well, to find out if that pattern is present at the end of the sequence, because each of these weights is not shared across time. Each of these weights in this layer, this feed-forward network layer, they correspond to a particular input time. And instead, we would like to look for the same thing across all the different points in time. If you've seen convolutional neural networks, which are one of the first models you can look at for doing deep learning for vision, you'll know that they have these weights which look in different parts of the images with the same weights. They use the same parameters to detect, is that pattern in the top left, as they do to look for it in the bottom right. And so we want to come up with a model that can do the same thing. Okay. So are there questions about that? I wish I had a good question to ask you guys to challenge you back on that, because that was a lot. Probably make more sense as we get into it. So following on from that, I want to introduce this complicated looking model, which is the recurrent neural network. And you'll see as we look at it that they importantly they kind of tackle those issues that we just looked at. So one, they can process sequential data, and two, they share the weights across time. So for each different input time step, we're going to use the same weights to look for the same patterns, basically. So here's how this works. Initially, we've got some input. We've got this input sequence. That's these 4 input variables here. So this is like maybe 4 different words. These are the word embeddings. So the embedding for word 1, for word 2, for word 3, and for word 4. And I've got a sequence which is 4 tokens long. I take the first one and I make a weighted combination of those features. That is, again, I just combine the different input features, different embedding elements together to represent, hey, is this particular thing present? Is this particular thing present in the input? Is this particular thing present in the input? But then I also combine that with the previous, what we call hidden state. And so this layer here represents our hidden layers of a recurrent neural network. Previously, we had the hidden layers of a feed-forward network were the ones in the middle, but now we're kind of, the forward direction is upward, whereas here the forward direction is from left to right. Input comes in, it goes into the first hidden layer, and we'll see in a second it can come out the other end, and that will be the prediction. So what I've done is I weight all the inputs, and then I also weight all of the previous hidden state, and then I add some offset. And then I take the activation of this. This tan H here, typically the activation function used in recurrent neural networks, again, just any nonlinear function. Maybe sometimes you use ReLU, but tan H is normally used in these recurrent neural networks. But importantly, like the way to think about this is just what this sentence says, right? So I've tried to color code it so it's more useful, but the hidden state is the activation of a weighted combination of inputs at this time step and a weighted combination of the previous hidden state plus some offset bias.
It means the embedded matrix of the previous would influence the activation.
That's exactly right. Yeah, the previous, the hidden state that came from the previous word, or in fact all the previous words, will influence the next state. And so when I'm computing this, the hidden representation, the kind of internal memory of the model for this recurrent neural network at step 4, this thing here is a combination of, hey, what's the latest input I received? What's the fourth word? And what was I thinking up to this point so far? That thing is based on the input at time step 3 and the time and the hidden state before that, and so on. The question? Sorry, why is tan H used? I'm not exactly sure what the reason is, but one thing that I think might be useful is that tan H can like flip the sign, so it could take an input and make it negative. It could take an input and make it positive. So I'm not sure. Maybe that has implications for like negating in sentences. You know, he was not doing this. That's probably a speculation though, so I don't really know. It's just seems to work better empirically. Question?
Exploding hidden state. So tan H would always bring it back to the center.
Yeah. Yeah. I think, yeah. There is some issues here with, there's some issues with these recurrent layers in general, and we can look at more interesting recurrent models later. I won't talk about it now, but the LSTM is like a better performant neural network layer, and basically we're just doing this to show you guys an introduction to language modeling, because next week we're going to look at transformers, and this will no longer really be relevant, but it's a much more complicated model. So if you can understand this, then it should let us get a foot in the door. We'll pause here for a second, and yeah, I think just like let it mull over. I probably missed some things, so let me know what I'm missing out, and we can talk through that.
You didn't say is what you don't learn. So what do you learn now?
Yeah, let's talk about that step actually. So this is just the middle layers, right? It's just some kind of, you know, I don't have an objective here. I haven't scored anything or calculated how good or bad this model is because I haven't given it a task, anything to produce, which is what you're saying. And so from those hidden layers, you can then add another layer, which basically combines a hidden state into a classification. So just like in the same way as a neural network has a final model head, which combines the last hidden layers into maybe the logits for a classification, a recurrent neural network layer can have the same thing again. So here I've got a a 2-layer neural network that is one transformation to get the hidden state and one transformation from that to get the output classification. And so you can, that can be whatever you want. Question? The live stream is crop portion of the stream. Thank you. That's an issue. This is because of this lecture theater, I think. Well, not ideal, but We've got to be fair. Okay, hopefully that's still okay for you. Can you really see in the light? I mean, I can't see it from this lighting, but maybe it's okay from your position. All right, just don't hesitate to let me know if there is if it could be improved. All right, lower lights, raise your hands. Okay, lower lights. All right, cool. So basically, given any hidden state, you can do a similar thing where you have a set of weights, which goes here from the hidden to the prediction, so I've called it WHY. It combines the features in the activations in the hidden state to produce some final output. And again, it shifts it by some offset bias. That's how you get predictions from these recurrent neural networks. Question?
Is there any reason for why all the words will share the same weight, or when you move to Y to the state?
Well, the idea there is that this weight here, this WXH, the one that takes in the word embedding and creates the hidden representation. The idea is that these recurrent neural networks, you want them to share weights across time, because essentially what you're saying is look for the same patterns regardless of where they appear in the input sentence. You don't want to say look for a particular set of words that appear near the beginning with some weights and have the same weights but in a different parameter look for the same thing at the end, because that would be very inefficient. So by having these blue weights at every point in time, you're essentially doing that. You're looking for the same patterns in the input, and so different words will contribute to the hidden state in the same way, regardless of where they appear in the sentence. What will change is how the model represents them so far inside the hidden state, because that gets changed over time by these other weights, WHH.
So you think about the efficiency of
Yeah, it makes things a lot more efficient. Yeah, it makes things a lot more efficient. Parameter-wise and just like ease of learning wise, because it's hard enough to learn the parameters. You don't want to have to learn them at the beginning of the sentence and the end of the sentence, and the middle, and every possible other combination that they could appear in. These are not very sophisticated models, but it just it should highlight a good introduction to language modeling. Yes.
I think the other problem for the constant weight is because of we are trying to avoid the overfitting of the model.
Why do you think that would help for avoiding overfitting?
Because if you have a variable weight for different tokens, then for every increase of the tokens, you will treat the training sets as more overfitting models for the training sets. Then these weights will remain for some characteristic for the training sets, but not for the consequence uses for.
Yeah. Do you think that's the same thing as in general? Like when you have more model parameters, it's easier to overfit. Is that the same point?
It's about like 50% pruning and pre-pruning and post-pruning.
Cool. Well, we won't get into the specifics of that, but let's talk about it in the break. Or is there anything else I should mention here? Cool. Okay. So as long as you get the rough idea, I think it'll become more clear when we look at the shapes, when we look at these models. But question? Yeah, what's the first hidden state? Yeah, so the way they work is, yeah, we have to initialize the first hidden state, typically fill it with zeros, and then we'll go from there. So moving on from that point, we'll combine the input of that time step with the previous hidden state. But for the first one, we'll have to initialize one as well. Cool, great. So then we can produce this prediction depending on what the data set is. Now, one thing that's really nice about recurrent neural networks is, as I've written here, you can process sequences of varying lengths. So regardless of whether my sequence has 4 tokens as here, or whether it has 100, the same parameterization works, right? And that's another reason to keep the same weights for different tokens, because otherwise you might be learning a position-specific parameterization when that position doesn't occur in a lot of your examples, or you've got huge examples, and that just means like many parameters to learn. So yeah, these things will process sequences of varying lengths. And you can also format them in different ways to tackle different kind of problems. So you might have I'm not quite sure what you'd use one-to-one off the top of my head, but you might have an input output which is one-to-many. So you take in one image, you output many different points in a sequence. For example, that might be image captioning. You've got an input image, you output a sequence of tokens, which all depend on the previous token generated to produce a final output sequence, which contains many tokens. Many to one and many to many. Anybody think of any examples for those others? Many to one, many to many.
Many to one would you say you input a video and it tells you video like
Yep. So yeah, many to one could be video classification, or so that would be kind of sequence classification. So maybe also like sentiment analysis would be the same kind of thing. You've got a sequence, you produce a final single output classification. Great stuff. Any other examples?
Is ChatGPT many to many?
So ChatGPT is not as simple as this, but yeah, the input and output is many to many. So many input tokens, many output tokens. And so yeah, this language translation could be something similar, similar that you might see in many to many, which would be a similar kind of thing. The way that for example, ChatGPT works is it's actually got something more like a many to one, which produces a encoding, and then you've got the opposite, which is a one to many, which kind of decodes that encoding, but not with a recurrent network, with a transformer instead. Cool. Any other examples?
Like segmentation in the video.
Uh-huh.
So train, we need to make segmentation.
That's a great example of many to many. Yeah. So video segmentation. You've got many frames of a video. Those are your inputs, and in the output, you've got let's say with the example of object detection, just for those not familiar with segmentation. But in the output, you're predicting the bounding box coordinates for the image, or you could just be predicting a classification at each different frame in the image. Cool. Great examples. So you can format it however you want. Your recurrent neural network might be hard to train though for some of those more sophisticated problems. Almost none of the state-of-the-art models are using recurrent networks anymore, which is why, as of tomorrow and moving on, we'll start looking at sequence-to-sequence models and transformers. But today, we're going to stick with an example of doing this many-to-one style problem to learn how to predict the next token, okay? And so that is the task of language modeling. Language modeling is, given a sequence so far, what's the distribution over what's likely to come next? And so in our case, this one output that we have is going to be a probability distribution over those different possible tokens in our corpus, given the input sequence so far. And hopefully by showing the model lots of examples of, okay, here are the sequences so far, which I want you to process and come up with a hidden state at that point, and then classifying the next token, we can learn to create a model which has that internal understanding of language. And once it's trained, we can basically just ask it, hey, we can maybe give it a starting prompt token, start with this letter, and then do forward pass on that, come up with a classification. And then you can just pass in this whole sequence so far. Every time producing a new sequence, adding it to the input, and then passing that thing through the model to come up with, okay, how would I generate a new sequence? That is the task. Any comments or anything you want to mention else about these kind of models?
For instance, if you wanted to develop a model that tells prose from a poem, would you use this kind of thing? Because it's kind of classification problem where you perhaps use prose-centric to distinguish. But would you still use this structure for processing things?
I'm not sure. Well, I'm not sure what the state of the art is anyway. Let's look at it in a sec. Let's look it up. But yeah, in general, you can do anything you can formulate as a classification. You can do that in just the way I've described, or you could do regression as well if the output was a scalar. Sorry, did I answer the question or not? But like,
Yeah, no, the question here, which approach would you use to develop a network that when you feed in, I don't know, 100 words, it tells you whether it looks like a prose or a poem?
yeah, so in that case, you could use a many-to-one to do a binary classification. I think that would make sense. Yeah. Yeah, so one thing that's nice to mention here, just specifically on topic of language modeling, is that language model datasets are like self-supervised. If you've got all the text, then you also got all the labels, because the label is just the next token in the text. So you don't have to have anybody prepare in advance, hey, please can you label this as prose or a poem, or label this as positive or negative, or whatever else. Instead, the dataset supervises itself. It contains both the features and the labels just in the raw body of text, which is really nice because it means it's very easy and cheap to get large datasets. For example, 40% of the internet might be your dataset. Okay, cool. So I'll leave you guys to read on to these limitations in detail if you want, but just to cover them in detail. Recurrent neural networks can be difficult to train, especially for long sequences. You can imagine that as you get further and further away from a word which should relate to this one, most of the meaning captured here in the early hidden state is lost. So when you end up at the end, you might not be able to retain that dependency between the two. Yes, that's the same thing as the long-term dependencies. They might be very sensitive to how you initialize them, and one thing that's really annoying about them is that they are very expensive to train, because to calculate how you should update your parameters, which appeared, let's say, early in the model here, how should you update these parameters? You need to process these t different time steps, and when you do the backpropagation, you need to also process t different time steps backwards. So everything's got to be done sequentially. You can't process different parts of the input in parallel like you could do with images or tabular inputs. Instead, it needs to be done sequentially, so they can be very slow. Is there anything else to mention? Yeah, and it can be difficult to interpret their results as well. So if you're looking at the hidden state in the middle of the network, what does it really mean? It's hard to tell. Hopefully, attention, which we'll look at tomorrow, should make that a little bit clearer. So just before we jump to another notebook, I just want to describe one thing which is called teacher forcing. So teacher forcing is where during training, instead of passing out, if we're, for example, generating a sequence, if you have a data set where the label is many different tokens in order which should be predicted, instead of starting off the next input being the one predicted by the model, so you're going through time, model predicts a new token, instead of taking that as the input, because it might be wrong, you force the label as the input. So if you see teacher forcing, that's what it refers to. It can make it much easier to train models because it keeps them on track. Whereas if you have say you have a random model initially, it's going to output a totally random token to start with, and that means that it's going to be very hard to predict the next correct token because your input previously was incorrect. So read about that if you're interested in that at the bottom of this notebook. I want to move on to get hands-on with this stuff. If you want to jump into building a simple character level language model, what we're going to do, the aim here is to build first language model to generate rap lyrics or whatever lyrics you want, catch your own. And we'll understand how to implement recurrent neural networks in PyTorch and get familiar with PyTorch's embedding layer, which we've talked a lot about, but we haven't really used yet. So here is this diagram of the language model. You have a sentence. You want to predict the probability of a next word over all the different words in your corpus. So you've got these many tokens, which in our case, as you guys know, will be a sequence of word embeddings. And the output is going to be a classification over the different tokens which you have. This language model, again, it's basically just it's a probability distribution over the next token. That's what it so So the first thing that I want you to do is to run this cell, and this will get you some data. It will get you all of the lyrics from these country songs, which are stored on my GitHub. There's other genres as well there. If you want to just look up this URL or look up my GitHub profile, or as mentioned here, you can just go and get some, like go to Genius and copy some lyrics and paste them in, or you could do something more complicated. But basically, this cell will get you a bunch of text. I'm going to run that, show you what it looked like. Just to look inside here, what it's doing is it's got a bunch of URLs, starts off with the corpus being an empty string. For each of those URLs, it gets the data at that URL, splits it by lines, removes the empty lines, and then joins everything by a space. And then it adds the lyrics from this URL into that corpus string. So eventually you end up with a big block like this. These are all of these country lyrics. And this is going to be my training corpus. So that's just one big string right now. First thing I need to do is to split that up and tokenize it. So in the next cell, I'm going to build this tokenizer. So the tokenizer is going to perform some steps like this. In general, this is roughly what most tokenizers do. They're going to clean it up. They're going to split everything. They're going to add special tokens like the start of sequence and the end of sequence. You don't need to bother with them here, but it might be a nice implementation. And then change those into token IDs. So these are going to be our token IDs. This is going to be our input to the first layer of our network. First layer of our network is going to be the embedding layer, which means it's going to take each of these indexes and replace them with the embedding for word 143, for example. So we'll end up with that data that I mentioned, which looked like a matrix of time by embedding dimension. So here's your challenge: is to implement this cell. We'll do 15 minutes doing that, and then we'll come back together. Move on to the next bit.
That would be, yeah, you have to like hold
Can you guys hear me all right on the mic? Does that mic work?
Yeah.
Yeah, cool, good. All right. Okay, let's do the code. So, so what do we have so far in the tokenizer? Just call it out if you've got it. Unique characters. How do I get that? Yep, you can call sept on the text, which I've got there. By the text there, I mean the whole corpus. I probably should have labeled it better, but that basically just gives me a set of unique items. There's many ways you could do this as well. So you might have different answers. If it works, it works. That's fine. Look up which one's more efficient. Vocab size. How do I get that? This is how many tokens do I have? Len of the unique characters. Yeah, that's fine.
That's set. Wow. What's that from? That's like inbuilt.
Yeah, that's a built-in Python function. Cool. So ID to token, a dictionary that maps from each integer ID to the token. Is there a good way to do that? There's many ways to do this.
It's going back a bit. It's not like the unique characters or unique words.
Yeah, the vocab is like a mapping between the IDs and the tokens. So the vocab is it's basically all your tokens.
Are we like separating things?
Yeah, in this case, we'll just do it like split on spaces. So we'll separate words into, we'll just do like a word level tokenizer. Split on white space.
We not get
Oh, sorry, no, I take this back. What we're going to do here is we're going to do a character level language model. So we'll just split everything into individual characters.
So it's set, split it up.
Yeah. So when you've got a string, for example, if you iterate through the string, it'll go through it character by character, and set, as you can imagine, as a result, gets every individual character as a different item.
And does it keep the space in space?
Yeah, it keeps spaces, it keeps punctuation, everything.
So the vocab is now set.
Yeah, exactly. Yeah. We'll print it in a second. ID to token though, how can I get that? Can we use what, sorry? We're not going to use the BERT tokenizer here. We're just going to go with something very trivial for demonstration purposes to get each character.
turn unique characters into an initial like list.
Yeah. So how would I do that? Can you give me the exact?
Right here, just open curly brace. Then you do and colon the nth item list unique characters.
So index to token.
Okay. For token in list.
Cool. Yeah, that makes sense. But I need the index. Yeah, don't I? So where do I get that from? Yeah, I can use the enumerate. Where do I put that? Outside of that, yeah. So if I enumerate through everything in that list, I'll get the pair of the, not just the token, but the index in the token.
You can drop the list now. You can enumerate.
Yeah, I could probably drop the list as well, so we can simplify this down. And we'll come back and do an even simpler one of those in a second, but how do I do the opposite of that? How do I reverse a dictionary in Python? To reverse a dictionary, I can similarly do a dictionary comprehension. So dictionary comprehension is like create a dictionary in one line. It's like a for loop, but all in one line, just like we did in the line above. So I want a dictionary. It's going to go from token to index for index token in all of the items which are in self.id to token. And I get them pairwise by doing items. Something like that. So if I now run, yeah, okay, I'll comment these lines out and run that and just check that that works. Create a new tokenizer. Like this, pass in the corpus. Tokens is not defined. I just haven't commented that line out, but if I print my tokenizer dot id to tokens, we should be able to see id to token. You can see that's what my ID to token should look like. So it's a list of these different integer IDs mapped to each a unique character that I've got now. Okay, cool. So there's a simpler way to do this whole line, which I believe you can just do it if you do. So everything that comes out of enumerate, I'm basically setting it as a key value pair of a dictionary. So I think I just use the built-in function dict to enumerate through all the characters like that. And I end up with the same thing there. So that's the simplest way to write that line, ID to token. Cool, so copy that down whilst you're doing that. This pre-processing, how do I lowercase everything? txt.lower, yeah, thank you. Just like that. Other pre-processing steps if you want to remove punctuation or whatever else. And then the token IDs. How do I get the token IDs out of my tokenizer here, given some text? So self.token to ID, great, that's a dictionary. So I want to pass in there each token and do that for all of my tokens. So I'm going to do a list comprehension to go through. So that's what I want. For token in tokens, in txt, right? Is anybody got any issues with that? Basically, yeah, just a for loop, creating a new list which contains the ID of the token, using that token to ID dictionary. And then the decode is a little bit more challenging. But the way you can do that is you can do join, of a new string, every string, like the empty string, has a method called .join. And that .join will basically join together everything that's in a list inside its parameters. So inside there, I basically want a list of the different, I want to pass in the token IDs, but I want to map them into their own tokens. So let's say the tokens go in there. I want to join the tokens by an empty space. That's what that line does. On the line above, I'm going to get the tokens from the token IDs. And the way I do that is by, I could say self.id to token. That's dictionary, which I want to pass in the token. For each token in my, each token ID in my token IDs. Let's just check that runs. What bugs did we get? Nothing. That seemed to work fine. Okay. So there's the solutions. Take a second to code that up and check that you can get the same thing. And in the process, just make sure you understand, okay, what are the tokens? The tokens are a list of those IDs. Make sure you understand what is the decoding done. It's taken the tokens, it's joined them together by a empty string to produce a new string. And what are my different ID to tokens and token to ID? They're the dictionaries which map between those two things in both directions. Yeah, sure. Sorry, I can't fit the whole thing in. But I assume you've got that so far. So that's the whole thing. Any questions about the Python there, let me know. The list comprehensions are confusing, I know. But the way to read that is basically like, it's like a for loop. And whatever you want out the for loop at each iteration is what goes on the left-hand side. So that is an expression which is the value inside each of these items in the list.
We do the set, we pass it to the set and then if anything preserved or
Yeah, the sets are unordered. So I'm not sure if a round trip gives you the same order. Try it out, let me know. I'm not sure. Okay, cool. All right, let's move forward. So if you haven't got that, take a picture. 10 seconds to do that. And then we'll move on. So given that we've got that tokenizer ready, now we need to basically create the language modeling data set. So the data set needs to consist of features, which are the sequential words in a body of text so far, and targets, which is the next token in each position in time. We're just going to do a character level. So we'll split it into characters. So each token in our case is going to be just one character. Might be punctuation, a number, or text. Cool. Yeah, in most cases, you're not doing character level because, you know, what you're doing when you do character level language modeling is that you have to learn an embedding for each character. That's like a vector embedding for each character. Well, that doesn't really make much sense because characters can appear in many different words and have many different meanings. And so that vector doesn't really capture the whole, it's not the most useful concept to represent the character as in a lot of cases. Whereas a word is like a discrete item, you know, most of the time at least, it's going to be used in the same context. Unlike characters. Cool, so now we got to create the data set. We've seen torch data sets before, and you know that they've got a few important methods which you always need to implement. One is the len, and one is the get item. For the get item, I just want you to get a random chunk from the data set of size, chunk size up here. And so you can use the random library to get that. So you can do a random.randint, for example. Figure out how that works. It's going to get you a random integer. I want that to be the starting position inside the data set. So this data set might be 10,000 characters long. Pick a random place to start. Return two things. All of the tokens up to all of those 30 tokens. And then the second thing you want to return is the next character. We'll also need to encode the text and store it as a tensor. That is to take the integers indexes using the tokenizer of the text which we've got in our corpus, and then also basically find what's the next character for each of them. I'll do this line because this line's not so obvious, but I'll give you guys a second to fill in some of the other stuff and have a look around that. Cool. This is a method that's the one you need to use for calculating the features. I'm just going to roll back all of the features by one character. So I'll use that in a second. Okay, so X should be pretty easy, right? X should just be like torch.tensor of all of the tokenized corpus. That should be the torch tensor of all of my tokens. And then I'm going to use np.roll to shift this in a certain direction. So how does this work? Okay, I've got this thing X. It's the numbers from 0 to 9. And I do np.roll. I specify a number by how much I want to roll it. And then that gives me the numbers like shifted in that direction. I think this method would work on a torch tensor. Try it. It might not actually. Not sure.
Implement the number sensitivity, like
It doesn't mean contiguous chunks. It can be like any random chunks. Sorry, are you asking about the lem method?
the length.
Yeah, for the lem method, just implement that as like the how many yeah, what would be the large number of contiguous chunks?
So if you get a 1,000 and
Yeah.
yeah.
So here's what I've got so far, just bit by bit. I don't know how this is going to work yet. So maybe something like that, but I want to roll things in the backward direction, I think. So we'll print that. Maybe it's wrong in a second, but I'm going to do something along those lines. See if you can figure it out before me. Self.vocab size. Does my tokenizer have a vocab size attribute? Yeah, it does. So what I'm going to do for self vocab size is just say tokenizer.vocab size. The length, that's going to be the len of self.x, rounded down by chunk size. And when I return something, I'm going to return, okay, I want to get my input x. Those are all the integers representing each token. I want to slice that from the starting index up to the starting index plus the chunk size. So if I start at index number 10, got a chunk size of 30, I want to go from 10 to 40. Remember in Python, this is not including the last index, so we 10 to 39 inclusive. And the label for that sequence, the next character, which I want to predict, will be self.y indexed at that end point. So start index plus self.chunk size. All right, I'll try and run this now. This is my lyric data set. It needs to take in the tokenizer. And it's got a default chunk size of 30. That's fine. And then when I run this, these things should work. Let's see what errors I get firstly. Seemed to work. Seemed to work fine. Let's just sanity check this, because this is the part I'm not sure about. That seems suspicious. So this is what my input looks like. Here's the sequence of tokens as a torch sensor. My label is a 31. I don't know what that is. So let's use the tokenizer to... Oh no, I've already done that. Okay, yeah. So here, the sequence so far is 3 go, verse 1, I don't. Next character, A. Not sure about that. I don't, 1. That doesn't look right. Should probably be an A there, right?
Yeah, I think like you're skipping over one character, but you roll and then you use that.
Yeah, you're right, actually, I mean, yeah. Yeah, so actually, you know, I could just forget this roll, couldn't I? I could actually just forget that completely, and that would simplify things. And then just get the next level X. Like that. That's much easier, isn't it? It's better. So run that. And now do things look okay? I don't want to run you over. I don't want to run you over. That's cool. I don't want to run you over. Why are they all the same? I don't want this. I don't want to go up to self.vocab size. I want to go up to the length of the whole thing, really, don't I? So I just say corpus length there.
Are your chunks overlapping or are they?
They're overlapping. Well, no, yeah, they can be. They're just random.
Yeah, I think the length total length minus the.
Yeah, the length.
The length of your data set will be the whole thing minus the chunk size, not including.
Yeah. The length doesn't really matter. Yeah, because yeah, I mean, if you wanted to have contiguous chunks, then you could. That would be an accurate length size. But in our case, like, there's not really much point to finding. Okay, here's how you get item number 1, number 2, number 3, number 4, number 5. You can just get around 4.
Yeah, that's true.
It's just, yeah, it is just not a point, to be honest. It's just an item requirement for a land, so roughly, how would I characterize the length of
I don't know if the length at all.
the data load is the data load when we go back to this make sure that we no, sorry, we're trying to test split.
I just split up the.
Yeah, I need to remember those spread that they all are to test and I'll test it. But actually, data load does mean to right because when you iterate the data load, it will only go up to. So what we're saying that we have a length is basically roughly how many chunks will fit in the data set. If it's saying that's how many chunks you try, we'll call that. You know that is just random sentence.
That's how many we're using for the different. So that's just the number we'll get thrown in for now.
That'll be the number of sequences we make just for each. We'll call that one run through the whole list, even though it's not
Actually right from the target, you don't want to connect.
Okay, I think this looks right now. So here's what I've done.
So you have one minor each case of if you stick an index really close to the end, near the end of compass length, then it's going to try to assess some random variable. That's how fine it is.
Yes, actually that's a problem, isn't it? So if I were to try and iterate through all of this, I could say, hey, the starting index is the very last character, in which case I can't go up to starting index plus self.trunk size. So I should probably only start at self.corpus length minus self.trunk size.
Yeah.
Minus 1 from that as well. Yeah, does random include both? Yeah, including both endpoints. So yeah, subtract 1 as well. Might be some other bugs we need to come back and fix later. Sorry? Yeah. So with this point on like the len is not accurate. I know, guys, but it's okay. Like, it doesn't really matter that much. All I'm saying here, and all this will be used for, is basically how many chunks of data should we call one epoch? And so I just thought this was a fair way to define it. Basically, if they were contiguous chunks which stacked up end to end, how many of them would there be? In the case they're actually just randomly picked chunks. But you are right, it is wrong. Okay, cool. I'll move on in a sec in the interest of time. So grab a picture if you need it. There's probably bugs in it as well, but I'll share the answers after this. So we've got these chunks of data. Cool. Yeah, it looks good now. All right. Data loader. How do I create a data loader? I've got this data loader from torch.utils.data. Create this data loader. And inside goes the data set. Is that what I called it? Data set. Yep. It also has a batch size. I'll say 16. And shuffle equals true. That should be good. All right, so this is what the first batch of data looks like. My X is this big tensor. And my Y down here is this tensor. What are their shapes? Well, this one is the length of how many items I've got in the batch. That is a label for each item. That's the next character, its index. And here I've got all of the characters in the sequence so far for each of those 16 items in the batch. So this is the sequence of characters in the first item in the batch, second example in the batch, and so on. Cool, so that one's pretty simple, right? Just create a data loader, pass in the data set, pass in the batch size, and shuffle. Following on from that, we need to define the recurrent neural network model. So here, this diagram highlights that we've got token indexes to start with. These are the indexes which represent the different words. And the first layer is actually going to be the thing which gets these embeddings. So we're going to need to use this embedding layer, which comes with Torch. So find the details of what we need to do there, but I'll kind of talk through this step by step as we go. So here we'll define the initializer, and in there I just need to do three things. Define the embedding, define the recurrent neural network layer, and define the classification head. So take 5 minutes to do that. Read through the section above because you'll need to know exactly what the sizes need to be, and then I'll write that. Okay, so let's imagine I have no idea what the embedding layer is, right? What do? Look it up, Torch, embedding. Find it here. It says this is a simple lookup table that stores the embeddings of a fixed dictionary and size. Usually used to store word embeddings and retrieve them using indices. So that's what it does, right? We give it a list of indices, it returns us a list of word embeddings. So it takes these parameters, number of embeddings and embedding dimension. Those two are the ones which are required. The others are optional, as you can see. And so you can choose this. You can choose the embedding dimensionality you want. The bigger the embeddings are, the more rich the representations of the word can be, but probably the longer it'll take to train. You've got more parameters to update. Might be harder to train as well. And then you've got the number of embeddings as well. So this is how many words, this is our vocab size. So let's go and implement that. It's going to be torch.nn.embedding. It's going to take in the number of embeddings. That is self.vocab size. And it's going to take in the embedding dimensions. That's going to be the embedding size passed in as a second parameter, like that. Now we've got to initialize the recurrent neural network layer. Look this up. Torch RNN, it says it applies a multi-layer RNN with a tanh or ReLU nonlinearity to the input space. There's the equation that I showed you earlier. Mine actually only had one bias. They're all combined in the same vector, but doesn't really matter. And so here's the parameters needed. Input size, hidden size, number of layers, and then you can have the others as well. But basically, this input size is how many inputs do I take into my recurrent neural network layer here. Basically, what's the dimensionality of each input? In our case, that's the embedding size. The next parameter is the hidden size. So that's basically what have I chosen the dimensionality of my hidden representation to be. So the weight between these two, x WXH, I called it above. That thing is going to have size hidden dimensionality by word embedding dimensionality. Next thing I need is number of layers. So I haven't mentioned it yet, but you can actually have stacked recurrent neural networks, which are basically not just one layer of hidden layers followed by an output, but maybe potentially many hidden layers. And each of those hidden layers in the same horizontal position in my diagram, they get computed at the same time step from the previous hidden state. And then the next hidden layer will take in the output of its previous state from the last time step. We'll keep it to a single layer recurrent neural network now, but one thing you do to quite massively increase the capacity of your model is just increase that parameter. Make it deeper, makes the model more powerful. I found like pretty significant performance improvement when you increase the layer size to 2 or 3. Didn't try it beyond that. So that RNN layer needs these things. I can use it like this, torch.rnn, torch.nn.rnn. It takes in the input and then the hidden size and then the number of layers. So the input is going to be the embedding size. The hidden dimensionality is going to be the hidden size passed in, and then the number of layers I'm going to say is this n layers, which is also passed in. Then finally, I've just got this classification head. This classification head is just going to be a linear layer used to make a weighted combination of the features, and that produces the logits. That's the unnormalized probability distribution output by the recurrent neural network. So the way this works is it goes from the hidden size, because it's taking the current hidden state and combining them to form a vector with size, vocab size. And then that should be the initializer done. Let's just initialize it, make sure that everything runs there. So RNN is equal to that. Let's do RNN dot embedding dot weight dot shape, so we can see what the shape of the embeddings is, and we can play around with a few other things there as well. In it missing 3 required positional arguments. Oh yes, it needs these 3 things, doesn't it? The vocab size. So where do I get that from? I think I've got my tokenizer has a vocab size attribute. Tokenizer.vocab size. Next thing it needs is the embedding size. I'll say that's 128. And the hidden size, I'll say that's 256. My embedding weight.shape seems not to have worked because I've missed out this to do, initialize the parent class. Got to call super. Gives me an object with all the attributes and methods of the parent class. Super.double_init. That's going to initialize it like that. Run that. Seems to work. That's cool. So the embedding weight shape is 50 by 128. Does that make sense? Is that right? Nod of heads? Yeah, shake of heads. Makes sense because my embedding dimensionality is 128 and I've got 50 different tokens. So this weight matrix that comes in the embedding layer is basically just a matrix where each row is a different word embedding and each column is the, well, across the columns you have the different embeddings. Cool. So that's that layer. Coding away furiously. I like it. Nice. Actually, no need. I've done it for you in the next cell. So here's the solution. I missed one thing there actually, was this batch first. You can toggle this or not, but one thing about the recurrent neural network layers and other recurrent layers in PyTorch is that they break my golden rule. My golden rule, which is the first dimension in PyTorch, is always the batch dimension. For recurrent layers, they like to have the time dimension first, but you can toggle it and refit things around. Depends on the format your data comes in. It might be easier to have it in such a different format. So here I've set Batch first true, just because that's how I've decided to implement it below. After I did it, I realized that'd probably be better the other way, actually. So I see why they did that. But just be aware of that. You need to set that. I've got to initialize the hidden state as well. So, got to figure out what size that needs to be. In my model, how big is this hidden? How many parameters are there in the hidden state? What's the shape of it? If I go with these default parameters here. Sorry? Sorry, what did you say?
Is it 256?
256. So where do you get 256 from?
So previously you wrote
Let's just stick with these parameters.
yeah.
So in this case, the hidden state is going to be how big? 32 is a good start. It's definitely going to have a 32 in because that's the dimensionality of each hidden state. The question is, well, there's a few questions now. One is how many hidden layers do I have? That's going to be another dimension of the hidden state. And the other thing, which you need to specify when you initialize the hidden, is basically what's the batch size? How many examples am I trying to look at, which I need to initialize the hidden state for? Again, we can find this out in the RNN layer. Scroll down here. The inputs at any given step to the RNN layer, when you call the RNN layer, which we'll do in our forward. So when I call self.rnn on some data, it actually takes in two things now. Not just the input data, but also the previous hidden state. And so I'll need to initialize this and pass this in as well. So this thing, it says it's got shape like this. D times num layers by n, which is the, what is that one actually? N is the batch size, and this is the hidden size. This D, don't worry about that, just treat it as 1 right now. But if you're interested, you just look at bidirectional neural networks. Come from both directions. So ours is going to be number layers by number in the batch, by batch size, by hidden size. So I'm going to say torch dot zeros, and there I can specify a size, I believe. So the size is the first parameter, so I'll put it in a tuple. And in that, I'm going to have self dot, what have I got? Self dot num layers, batch size, and then self dot hidden. What was that? What was that again? Yeah, num layers. Then the batch size, which you can see I've passed in as the first parameter to this hidden method, to this init hidden method, followed by the hidden size. Okay. If I run that, we'll print the hidden size for a batch size of 2. And we should see its length by batch size by the hidden size. So 1 by 2 by 32. Is that right? Oh, sorry, that's layers length. Yeah, so I've got one layer, I've got 2 different items in the batch, and I've got 32 dimensions for each of them. That's the shape of this big tensor, which makes up the hidden state. And then the final thing we've got to do is the forward pass. So again, next cell, you'll find out how to do that. But here, this diagram is a really important one to understand. So this diagram shows what comes out of the call to a recurrent layer in PyTorch. 2 things come out. All of the outputs, that is the activations in the last layer of the recurrent network, which might be stacked, like in this case, and the hidden states on the last time step. So you might be thinking, why does that happen? Of course, I just want the output of the last one, but there are many different models which might use these things differently. So something might take the representation in all of the final hidden states, or something might take, or you might want a particular prediction at a certain point in time, so you take that time step. But both of these things come out. And so this is roughly what the forward methods looks like. So using the rest of what's here as a template, you guys have a stab at implementing that and see if these things look correct when you print it out. After we do that, I'll implement the final, I'll implement the generate method, because that one's rather complicated. So I'll just copy that in for you and give you the answers. And then we'll run it and see if we can get some lyrics out. Take 5 minutes to do that.
I didn't really have time to go to training with that website. With you can have a PowerPoint version for example, like one we have about because you've got a prediction, you just have to you've got a loss. You just have to averaging and then average. That loss, they'll basically they'll do the correct. Yes, so the back complications, specifically the other actions, are hard to get. So if you look at the Piano neural network, if you look at the equation, very neat about the loss of stuff in point 1 and point 2, it can tend to stay. So if you have a two one of those two very complicated. You don't want to calculate time is every time it says you want to catch that. But that's us. It's different by the fact that like you're not only going back to the model different, like in my diagram of status, you're going from the output to the input, but also going from the output to the inlays backwards. Not the input, and that would be fine. Right? The idea of it works, you're also saying yes, it is like so yeah, just say
Okay, so does anybody think they got the forward pass? How do you do this part? How do I call the embedding on my X? Self.embedding on X. That's right. Very simple. Not a trick question, that one. What about the RNN layer? How do I do that? Self.RNN, call it on the embedding. That is going to be part of the solution. Look at the docs again. Forward method of the RNN requires two things. Requires the input, as usual, but it also requires the previous hidden state. So, do you want to finish that off? What do you think goes in here, second parameter? What was that? Phone a friend if you need. Self.hidden goes in there. Yeah. Cool. Good stuff. Good teamwork. Yeah, that's right. So those two things, that's what you need. Exactly. One there, one there. So the RNN is going to take in those two things. It's going to take in the embedding. That's our X. And it's going to take in the hidden state from the previous time step. Combine those two things with two different linear layers, concatenate them, and that is your, and that basically produces your next hidden state. What this does when you call it though, because these embeddings contain like every time step, this runs the whole RNN from end to end over your whole sequence. And that's what you get, like more than just what's in the next layer come out when you do this in Torch. So when we did a linear layer, we just got like, okay, what's the output of that linear transformation? When we do the recurrent layer, we give it the whole sequence, and it goes through the whole sequence, computes the hidden state for all of them, for every hidden layer, which may be stacked deep. And then the output, and then it gives you these two things as the outputs. These outputs, as shown above, that's the hidden state of the last hidden layer for every time step. So in our case, if I've got batch size 3, hidden size, well, you can imagine the output is going to be batch size by sequence length by hidden size. So for each of the batches, I've got this many outputs, and each of them have that hidden dimension. And then the other thing that comes with the RNN is the hidden states at the last time step. These are basically the final encoding of the model's memory of what it's thinking at that point, right? So what is currently stored in the model memory? That's the hidden values there. So those two things come out there. We don't actually need the final hidden. Well, actually, I could say that about the outputs as well, because those two things both appear in both of them. But we just want this thing. That's the thing we want. That's the hidden state of the last layer. And we just want to apply a linear transformation on that to calculate the classification logits. So we just call self.classification head. On that. On the outputs, on the last thing in the outputs. But I want all of the batches. I just want the last output. Is that the right size? I'm not sure. What comes out of this thing? Outputs. Output, tensor of size, number of layers by hidden dimension. What's that?
That's fine. You want the next one? Where the,
This one?
no. When batch was sequence.
Oh yeah. Okay, yeah. So that's when batch first equal was false. Thank you. This is what I'm doing. I've got batch first equal true. So I want what do I want? So that's my number of layers. Yeah, I just want the last layer, don't I? So I should just be able to index it with a -1. So I want the last layer. If I index something of that shape by the last layer, I'm gonna get a shape which is this, right? It's gonna be the these are so confusing, all these things. It's gonna be sequence length by hidden size. Is that what I want? No, I just want the last one, don't I? Yeah, so actually I do want all of the batches. So that first dimension is the batch size. So I've got batch first equal true. So I want to get out all of the batches, but just the last layer of the but just the last output. Sorry?
But you only got 2 bytes.
Yeah, and it will get all of the other ones without indexing them out. Okay, so let's see if that works. Let's see if we can do at least one forward pass. If we get that, then we can understand the insides of the model. All right, does that look okay? What's the size that I've predicted down here? Prediction.shape. Makes sense, right? That shape makes sense. 16 by 50. I've got 16 different items in my batch, and I've got 50 different numbers for each of them. Those numbers represent the unnormalized probability distribution over those 50 different possible tokens. And the batch size is 16, the sequence length is 30, the vocab size is 50. Great. So I've removed the last item from there in that 30. So now we're running at closer time. So I'll go through the solutions which I've already got prepared. Come on. All right, so sorry, this is being extremely slow. So let's go to the bottom of this notebook. This contains everything that we've written so far, and it also contains 2 new functions implemented, which are the function to generate new text and to train the model. The train the model actually looks exactly the same as you've seen, so that one shouldn't be too surprising. And the generate text, what this one does is it basically gives the model a starting prompt character, and then it asks it to continue from there. This is the training function here. It just does the usual stuff you've seen. It goes through the data loader and iterates through the batches. I'm going to try and run everything in this notebook above. And here's the generate function. So it looks rather complicated. It's basically just making sure the dimensions match, because your model always expects there to be a batch dimension. You need to make sure that that's not in the place of the length of the token. Of the length of the sequence. So you need to make sure all of those things match up. Now, if I can get all of this to run, being horrifically slow, then this should be able to generate text, and you'll be able to see how well the model trains. So I'll leave you guys to explore how that function works. But what I want to do, all I want to do is scroll to the top. All I want to do is scroll to here and start TensorBoard. That doesn't look like that's happening. So let's try and do this from the terminal. Mm. Oh, wow, okay. Oh, I can't believe this. There's usually a little button there and it's frozen and it's not loading in yet, so this is going to take a while. So if you run this notebook, which I'll send you in a follow-up to this, you should see pop up in TensorBoard the training curve over everything that's happening, and you can see the model loss going down and down. And then finally, you'll be able to see we've also logged the text generated for each different epoch. So I'm trying as hard as I can to show you that now, but my laptop is really dying. Thanks to everybody streaming this. So let's try and copy this into into the notebook, see if that works. All right, we've got the code in there. Run all. See what happens. See if we've made any mistakes. Well, now you can see it's training. Model's training. Loss looks to be going down gradually. And I believe if we can open up TensorBoard in here, then you should be able to see the generated text.
Can we reduce the number of epochs?
What was that?
Can we reduce the number of epochs?
What about the number of epochs?
Reduce it.
Though
it may be a bit unconvincing, but we can do that.
Well, we're actually logging it as we go. So it's just in TensorBoard. I just need to do TensorBoard, what is it? Load X TensorBoard. This is horrifically slow. Let's try command again. Sorry for the delay, guys. Okay, right, we're trying multiple avenues here. I'm trying to do it in VS Code. I'm trying to do it in Colab. I'm sure one of them is going to work. Unless I launch another process running on my computer and it kills the whole thing. Right, I'll give it 2 more minutes and I'll let you go. I don't want to keep you here waiting any longer for my computer to hurry up.
Yes.
Okay, here we go. So here's the loss curve of this thing training over time. Nice shape. That's the kind of thing that we like. Going down exponentially. Try it with a bunch of different parameters. I found that a lot of them were significantly slower than these finals ones which I showed. Loss doesn't mean much though, right? The loss is just some arbitrary measure of is it doing better than it was when I first started training it. So what you really care about is what's it producing. And so in the code, I've got this add text function. And what it does is it adds text every time